We've been working with integrals for a while now, and I want to continue to talk about integrals and look at some very specific properties and some different things that we can do with them, different techniques to make life a little bit easier while we're integrating. The learning objectives for the next several videos. The first thing I want to do is talk about the idea of using odd and even functions to assist us in finding a definite integral. And I want to talk about the idea of the mean value theorem for integrals. I want to understand how to use it and what it actually means. And I want to find the average value of a function over a closed interval. So let's start off with the idea of integrating odd and even functions. First of all, as a quick review, we say that a function is odd if f of negative x is equal to a negative of f of x. Now, probably the easiest odd function to look at, or one of the easiest, is simply f of x equals x cubed. Now notice if x equals 2, then y is equal to 8. So if I evaluate this at a negative x, in other words, negative 2, so x equals negative 2, y is actually equal to a negative 8. So here's the f of negative x equals the negative of f of x. Now also notice that this is actually symmetric about the origin. Now, an even function, again as a quick review, a function is said to be even if f of negative x is equal to f of x. And probably one of the easiest even functions to look at as a quick demo is f of x equals x squared. Now if x equals 2, f of x equals 4. And if x equals negative 2, f of x still equals 4. So f of negative x is the same as f of positive x, hence it's an even function. Now if we identify f as being even, and we're going to integrate from negative a to a, then this integral from negative a to a of f of x is the same as twice the integral from 0 to a of f of x dx. Sometimes this is a much easier option to follow because whenever I have 0 as an upper or lower bound, it makes life easy to evaluate because I'm going to be evaluating some function at 0. And this kind of makes sense because if I look at the area under the curve, the total area, if a is negative, if negative a is this negative 2 and a is 2, the total area looks like this. But because of symmetry, if I simply find this area, I know that this area is exactly equal to that area. So all I have to do is take this and multiply it by 2. So if I multiply that by 2, I'll get the entire area. That only works because of symmetry. If I were to integrate, just to make sure that you're kind of following me here, if I was looking for the integral, say from negative 2 to 3 of x squared dx, this won't work because I don't have negative a to a. I go farther, I go out here to 3, I go clear up here. Now I could break it down as twice 0 to 2 plus 2 to 3, and I suppose there might be situations where that would be useful, but that to me that just made it more complicated. Okay, now if we identify a function as being odd, then the integral from negative a to a of f of x dx is going to be 0. And again, let me use this function here, or I'll redraw it real quick. So if I use f of x equals x cubed and negative a to a, from negative a to 0, I'm going to have a negative contribution. From 0 to a, I'll have a positive contribution, and these two areas are exactly equal, differing only in sign. So they will cancel each other out, and hence I'll get 0 as a solution. So let's go ahead and take a look at some examples of how maybe to apply some of these ideas.